Hi, I'm Paul Fulda from the University of Florida, and I'll be giving a brief overview of the simulation work we're doing here related to the LISA Optical Metrology System, or OMS. First, though, I'd like to point you towards 3 other talks at this symposium from our group members, which cover specific areas of this simulation research. Alex Weaver is presenting work on tilt-to-length coupling due to Zernike-based wavefront errors, and tilt-to-length subtraction with differential wavefront sensing signals. Paul Edwards is presenting some of his related work towards a high-speed computation method for calculating tilt-to-length coupling in the LISA long-arm interferometer, and Ada Uminska is presenting an ongoing simulation study in support of the experimental campaign at UF towards testing the LISA telescope prototypes for length stability. You can find links to these talks in the Related Talks section of this talk. Simulating the LISA OMS presents some rather unique challenges. At UF, like many other gravitational wave research groups, we have plenty of experience simulating the optics of ground-based gravitational wave detectors like Advanced LIGO. However, as you've probably heard by now, LISA is not just LIGO in space. Well, this applies to the optical layout as well as the data products and science targets. Simulations of the LISA OMS have to cover an extremely wide range of distance scales. We care about picometer precision measurements made using a 1 micrometer wavelength laser beam, which starts on an optical bench with a 1 millimeter beam size, before being expanded by a meter-scale telescope and traversing the 2.5 gigameter void between vertices of the triangular constellation. This makes finding any one simulation tool to cover the whole OMS very difficult. In reality, we have to use different approximations in different regimes, and depending on what aspects of the light path we're interested in at any one time. Right now at UF, our OMS simulation work is primarily geared towards what we see as one of the biggest challenges in LISA instrument science, tilt-to-length noise, or TTL noise. TTL noise describes any noise appearing in the path length measurements that arises as a result of angular fluctuations in the measurement laser beams. This can arise in many ways, but perhaps the most obvious way is from lateral offsets between the measurement axes and the laser beam axes. The figure to the top right shows how a lateral offset between the test mass center of mass and the measurement beam being transmitted to the far spacecraft couples any angular jitter of that transmitting spacecraft into length changes in the optical path between the spacecraft. We can estimate this TTL noise based on expectations for the level of spacecraft jitter and the level of residual alignment offsets after the AIVT procedure. The figure to the lower right shows the results of one such estimate. TTL noise could be the dominant length noise source above 0.5 millihertz. Of course, at this point we don't just throw our hands up in despair, we find ways to mitigate this noise. 2 ways under consideration right now are to actively adjust alignment offsets to minimize TTL coupling, and to perform coherent subtraction of witness signals that see the tilts, but not the gravitational wave signal. A decent approximation of TTL coupling can be calculated on a post-it note though, as shown here. So why do we need fancier methods than that? The truth is, the simple geometric TTL coupling is just one source of TTL coupling. We also have to consider all sorts of other small imperfections in the OMS that can cause other TTL couplings. It's also important to simulate this effect with high fidelity, especially if we're interested in performing coherent subtraction to gain an order of magnitude or more suppression. One method that we have been developing at UF is based around using Hermite-Gauss, or HG, modes. These paraxial modes have several useful features for modeling laser beams. First of all, they're incredibly easy to propagate. This is done simply by transforming the basis by adding to the real part of the Gaussian Q parameter. As a result, they can be used over a wide range of physical distance scales, which can be challenging for other methods like FFT propagation, for example. We also have lots of experience using these modes to describe the ground-based gravitational wave detectors, and the effects of misalignments can be well approximated by a simple coupling between different HG modes. One downside, however, is their limitation in describing high spatial frequencies and near-field effects. The lower central panel shows how HG modes can be combined to describe a top-hat beam, like the beam received by the LISA telescopes. We can model misalignments of such a beam by performing a coordinate transformation, as shown in the lower right box. We still have to actually calculate realistic photodiode signals though. This is done by integrating the optical beat signals over realistic photodetector surfaces, either analytically or numerically. Alex Weaver and Paul Edwards describe these methods in much greater detail in their own talks than I will here. So once we can simulate TTL noise, what do we want to get from the simulations? Let's return to the subject of TTL mitigation by suppression or subtraction. It's worth mentioning here that both of these are currently done routinely in Advanced LIGO. TTL noise is suppressed by actively sensing and controlling the core optics alignment, and passively by passing the input beam through mode cleaner cavities. Subtraction of TTL noise is also done in post-processing using the optimal Wiener method to find the best subtraction coefficient. And it seems that we may have to do both suppression and subtraction in LISA, although in a very different regime. Proposed suppression methods include using a movable clip aperture or beam steering devices to minimize the TTL coupling at source. Simulations will be important though to see how effective these methods are, and crucially to determine how to adjust these devices during the mission. There are several questions we need to answer about the coherent subtraction option as well. First of all, how good of a witness for TTL noise are the differential wavefront sensing signals going to be? Will a first order subtraction suffice, or do we need to consider bilinear couplings and higher order terms too? Results from Paul Edwards, Alex Weaver, and our collaborators at the AEI Hanover, shown in the lower right, suggest that we may indeed have to consider some of these higher order terms. And how do we find the optimal subtraction factor? Can any of this be done online, or must it all be done in post-processing? These are some of the questions we're working to answer. Another major difference between LIGO and LISA is that in LISA we don't have immediate access to the length measurement. In its raw form, the length measurement is completely swamped by laser frequency noise. Only after making the right time-delay-interferometry, or TDI, combinations do we get access to that length signal. This poses a real challenge for calibrating the TTL coupling to determine in which direction, and by how far, to move any active alignment components. The problem is compounded by the fact that the jitter of any one spacecraft affects 4 laser links simultaneously, potentially with completely different couplings to length in each case. New graduate student Don George is working with PEP Sanjuán to tackle this problem. They are studying how TTL noise propagates through the TDI combinations and testing methods to calibrate them to aid alignment mechanisms and for subtraction in post-processing. Considering only the science interferometer, there are 16 TTL coefficients, transmit and receive for both pitch and yaw for all 4 movable optical subassemblies. Here we show the TDI-X combination in its simplest form. The challenge now is to disentangle the different TTL coefficients, written here as K factors, by performing certain spacecraft maneuvers and analyzing the results. This can be complicated though, because the signals accompanying the TTL coefficients will all be correlated. Don and Pep have started to tackle this problem by building a fairly simple model with TDI, fixed TTL coefficients, estimated noise for the differential wavefront sensing signals, and so on, to understand the issues at hand and the scope of the problem. It's early days still, but it should be a project to watch out for in the future. One example of a non-geometric TTL coupling is via wavefront errors on the transmit and receive beams. Please see Alex Weaver's Symposium talk for some discussion of his work on transmit wavefront error TTL, or read this recently published open access paper describing the methods that we're using to calculate this. A similar analysis for the receive side of the telescope is in the works. As well as these dedicated simulation tasks, like any experimental group, we also use a variety of simulation tools to support our lab activities. Ada Uminska is presenting work at this symposium on simulating our telescope test structure using the Gaussian beam tracing software OptoCAD. We often use Finesse for frequency domain models of our interferometry experiments, for example as shown here analyzing the effects of residual amplitude modulation on Poundrever-Hall sensing of cavity resonance frequencies. A good resource to find out more about optical simulation tools developed by the gravitational wave community is gwoptics.org, maintained by Andreas Freiser, the lead developer of Finesse, and the links you can find therein. EFOCAD, developed at the AEI Hanover, is also a very powerful simulation tool that's been developed with LISA in mind. I've included an extra slide with links to these and other simulation tools in case you'd like to try them out for yourselves sometime. Thank you very much for listening, and please get in touch if you'd like to know any more.